All right, welcome to The Explainer. Today, we're going to tackle the single most powerful machine humanity has ever built, the rocket. We're going to deconstruct the mind-bending complexity behind how we actually escape Earth.
So, here's our game plan. We'll look at the big problem of spaceflight, dive into some classic physics, wrestle with a really tough equation, and see how engineers kind of cheat their way around it. We'll then follow the journey into orbit and wrap it all up with 5 key principles. So, let's get right to it, starting with the most basic question of all.
Okay, let's dive right in. To really appreciate just how incredible a rocket is, you first have to get your head around the unique and, honestly, the immense problem it's built to solve.
Think about it. We have these amazing, super efficient airplanes that can zip us across the globe. So why can't we just point one upwards? Why are they completely, totally useless for getting into space? Okay, this chart really puts it into perspective. The numbers here tell the whole story. It's not just about getting higher. A satellite in low Earth orbit is, 50 times higher than a plane. But the real kicker is the speed. It's moving nearly 40 times faster. But even more fundamental than that, an airplane's jet engine literally breathes air to work. A rocket, well, it has to survive and thrive in the total vacuum of space where there's nothing to breathe at all.
So 17,000 miles per hour. Let that sink in. Hitting that kind of speed and doing it where there's zero air for an engine to push against or breathe, that is the fundamental challenge of spaceflight. It's a common misconception, It's not really about going up. It's about going sideways, just ridiculously fast.
So how in the world do you solve a problem that big? Well, the answer, and this is what's so cool, it doesn't come from some brand new 21st century technology. Nope, it comes from physics that were first published way back in 1687. And this right here, this is the absolute key. A rocket isn't pushing against the ground, it's not pushing against the air, it's pushing against its own exhaust. Think about that. It's a completely self-contained system, and that is precisely why it works perfectly in the vacuum of space. The balloon analogy is perfect for this. You let the air out one end, and whoosh, the balloon shoots off in the other direction. A rocket is just that same exact principle, but, on a slightly more massive and explosive scale. It's why they work in a vacuum. There's nothing to push against, and they don't need anything to push against.
Okay, but it's not just the third law. This is where Newton's second law comes into play. F equals ma. So the third law tells us how the rocket moves. It gives us the principle. But the second law? That's the one that tells us how much oomph, how much raw force we're going to need to get that colossal machine to actually accelerate.
And this is just common sense, right? If you kick a wiffle ball, it goes flying. You kick a bowling ball with the same force, and you're probably just going to break your toe. It takes way, way more force to accelerate something massive. And that is the #1 problem for a rocket that's basically a giant can filled with hundreds of tons of fuel. So, when you put it all together, it boils down to this. If you're a rocket engineer and you want more thrust, you really only have 2 knobs you can turn. You can either throw more stuff out the back, more mass flow, or you can throw that stuff out the back faster, higher exhaust velocity. That's it. Every rocket engine ever designed is just a clever balancing act between those 2 things.
All right, we've covered the basic physics. Now we get to the really juicy part, the technical heart of this whole thing. And it all comes down to a single, beautifully elegant, and completely unforgiving equation.
This is it, the Tsiolkovsky rocket equation. It was figured out way back in 1903, and it is basically the final boss of rocket science. It dictates the absolute maximum change in velocity a rocket can ever hope to achieve. Every single rocket design, from the V2 to the latest Starship, is a desperate fight against the brutal math of this one formula. So let's break it down. First up is delta V. The best way to think about delta V is like the currency of space travel. You have a certain amount in your wallet when you launch, and every single thing you want to do, get to orbit, change orbit, head to the moon, it all costs a certain amount of delta V. And getting to low Earth orbit, that's a hefty price tag, about 9.7 kilometers per second. That's the goal. Next up, we have specific impulse, or ISP. This is basically your engine's fuel efficiency. It's miles per gallon, if you will. A higher ISP means you're getting more bang for your buck. You're squeezing more of that precious delta V out of every last drop of fuel you're hauling into the sky. And then there's the mass ratio. And folks, this is the real villain of the story. It's the ratio of your rocket's starting weight, full of fuel, to its final weight when it's empty.
And here's the vicious cycle. To get more delta V, you need more fuel. But more fuel makes the rocket heavier. And a heavier rocket needs, you guessed it, even more fuel just to lift all that extra fuel. It's an absolute tyrant.
And this chart, wow, this just lays bare the brutal reality of that mass ratio problem. Just look at it. 90% of the rocket's entire weight is just propellant. Then you've got the structure, the tanks and engines, at 6%. And the actual thing you're trying to get to space, the payload, a tiny little 4%. A modern rocket isn't really a vehicle. It's just a giant flying fuel tank with a tiny little satellite taped to the top.
Okay, so if the math is that brutal, how on earth do we ever get anything useful to orbit? I mean, it seems almost impossible, right? Well, this is where engineers came up with a really clever, almost brute force cheat to beat the equation. It's called staging.
The logic is pretty simple, but it's genius. You fire a huge first stage to get you going. But once its fuel is gone, you don't keep dragging that massive dead weight of empty tanks and giant engines with you. No way. You just drop it. You throw it away. That drastically improves the mass ratio for the next stage, which can now fire up its own smaller engine and push the now much lighter rocket the rest of the way to orbit.
The type of fuel you use is also a huge piece of the puzzle. You've got solids and liquids. Think of solid rockets like a firework. Once you light it, it's going to burn with incredible power until it's done. Great for getting off the launch pad. Liquid engines, on the other hand, are more like the engine in your car. You can throttle them up and down, even turn them off and on again. They give you the efficiency and the control you need for that final, delicate push into a perfect orbit.
All right, we've got the physics, we've got the math, and we've got the engineering hack. So let's put it all together now and follow a rocket on its incredible journey from the launch pad all the way into orbit.
So here's a typical timeline. The first few minutes of any launch are just a violent but perfectly choreographed dance of events. You have liftoff. Then about a minute in, the rocket hits something called max Q. We'll talk more about that in a second. A couple minutes later, boom, the first stage separates. And then, around 8.5 minutes in, you get MECO, main engine cutoff, as the second stage has done its job and you're coasting towards your final orbit.
Now, have you ever noticed that rockets don't just go straight up? Right after they clear the tower, they start to tilt over. This is called the gravity turn, and it's a brilliant move. Instead of fighting gravity the whole way, they literally use it to help steer them onto a horizontal path. It saves a ton of fuel and is way less stressful on the rocket.
Okay, so what is that max Q thing I mentioned? It stands for maximum aerodynamic pressure, and it is the single most terrifying moment for the rocket structure. It's the point where the combination of the rocket's insane speed and the thick lower atmosphere creates the absolute maximum physical stress on the vehicle. It's the moment the air is trying its hardest to just rip the rocket to pieces.
So we've gone through a lot of complexity here. Physics, equations, engineering. But what are the big takeaways? What are the fundamental, unbreakable rules of this game? Well, it really all boils down to 5 core principles.
Let's call these the 5 pillars of rocket science. Number 1, propulsion is all about action-reaction. You throw mass one way, you go the other. Number 2, you have to bring everything with you, your fuel and your oxidizer, because there's nothing in space. Number 3, the rocket equation is law. You can't break it, you can only work around it. Number 4, mass is the enemy. Always. Lighter is better. And finally, number 5, staging is your secret weapon to beat the mass problem. These 5 rules, they govern the very first fire arrows, and they govern the most advanced rockets being built today. They are fundamental.
And that brings us to today. With reusable rockets, we're getting really, really good at the engineering part of overcoming the rocket equation. But the equation itself, its tyranny remains. It still takes an absolutely staggering amount of mass and energy just to get off our planet. So leaves us with a big question. What's the next great barrier? What new law of physics will we have to master to truly expand out into the solar system?